Welcome along. Today we're going to be talking about the independence of two random variables. This example is taken from the 4th edition of Mathematical Statistics by Mendenhall, Wackerly, and Scheaffer. We have here a function of two random variables, y1 and y2. We see that it's equal to 2, and we see the range of these variables. y1 is greater than or equal to 0 and less than or equal to 1, and then y2 is greater than or equal to 0, but also less than or equal to y1. Now, intuitively, we might think that these are dependent upon each other. But as with most things in mathematics, our intuition sometimes fails us, and that's one of the reasons why we always seek to demonstrate these things. Now, you may recall that independence is an idea. It is a very strong idea, and if y1 and y2 and y2 are independent if and only if, so the strongest sort of statement we can make about this sort of thing in mathematics, if and only if the following is true. The joint probability function, y1 and y2, is equal to the product of the marginal probability functions of each of them. So if we can demonstrate that this is true, we will have shown that they are independent. And if we fail to show this, or if we are able to demonstrate that it's not equal, that this is not true, that this is not equal to each other, then we can demonstrate that they are in fact dependent upon each other in at least some way. So with that in mind, and that as background, let's go ahead and see what we can do about doing this. So first of all, we're given the joint probability function, f at y1 and y2, and we see that that's equal to 2 in that particular region. So all that really remains for us to do is to calculate the marginal probability functions for each one of these over that area and multiply them by each other and see if they equal that. So let's go ahead and do that. Marginal probability of y1. So consider again, y2 is defined as being greater than or equal to 0, less than or equal to 1. And so our limits of integration are going to be y1 down to 0. What we'll be integrating is the joint probability function, but we'll be integrating that with respect to y2. So what we see there is simply we have 2 dy by d2, which is equal to 2 y2 defined over y1 down to 0, which is equal to 2 y1, and we should again specify the range of those variables, or of that value. So that's our first marginal probability. So we're 2/3 of the way there. We have f at y1 and y2, and we have the marginal probability. Let's go ahead and get the marginal probability for y2. Now in this case, we see that y1 is defined from y, or from 1. Now this is important. It's defined as 1. It can never be greater than 1, but it's defined down to y2 because we've specified here that it's always greater than or equal to y2. We're going to go from 1 down to y2, not down to 0. It may go down to 0, but it's going down to 0 as it relates to y2. I suppose we don't really have to write this down again. I apologize. I will dy by d1. It's dy by, or dy1 is what we want. So again, just as above, that is 2 dy by d2. So what we see there, I did it again. I keep getting confused. There we go. The trick with a lot of this is to just pay careful attention to what we are doing. That's 2 by dy1, from 1 down to y2, which is equal to 2 minus 2y2. Now in this case, we know that 2, or y2, is defined between 0 and 1. Because again, it's less than or equal to y1, and y1 has a maximum of 1. So all that really remains for us to do is now look at the product of those two and see if it's equal to 2. See if we can somehow coerce it into that. So in this case, we have 2y1 times 2, 1 minus y2. And it does not seem as though there is any way for us to get that into any sort of a form that's going to permit us to have that equal to 2. We could solve this for certain values for y1 and y2 that might equal 2. But in order to demonstrate true independence, we need to see that they are always the same. So then we can say that the conditional, with the joint probability, I apologize, that is equal to 2 from above, and that does not equal f1, y1, the marginal probabilities of each one of these. Therefore, y1, y2 are in fact dependent for at least some values. But I'll just say in the range. Hopefully this was helpful. Come on back next time and we'll look at some other examples of marginal probabilities.